We're back with another exam walkthrough from 2021 October, Unit 4, Capacitance, question number 7 and question number 14. You can try out the question yourself and then watch me solve it. And for the March 7 examiner report, you can go to the end of the video. So let's try question number 7 first. A battery of EMF V is connected to a capacitor as shown. The capacitor is initially uncharged. Work is done by the battery to transfer a charge Q from one plate of the capacitor to the other plate. The final potential difference across the capacitor is V, which row of the table gives the work done by the battery and the energy stored by the capacitor at the end of this process. So work done by the battery is going to be equals to Q times V. Okay, so that's the formula that we know from our AS level as well. And then the energy stored by capacitor is going to be equals to half of that, basically, so half QV. The other half of the energy is lost. Okay, so the option that matches this is going to be C. Number 14, you have the train on the model railway is powered by contact with the rails. The train sometimes loses contact with the rails. The diagram shows a circuit that can maintain power for an electronic controller on the train even when the power is disconnected for a short time. The switch represents the contact between the trains and the rails. Okay, so we have this circuit which is representing the situation that's presented to us in the question. And when the switch is open, that's going to tell us that the train and the rails are going to lose contact. And when the switch is closed, the train and the rails are going to come into contact again. And then in part A, it tells us, explain how the circuit can maintain power to the electronic controller if the switch is opened for a short time. So first of all, when the switch is closed, your capacitor will be charged. It will store electrical energy in the form of electrical charge. And along with that, one important thing to recognize here is that the potential difference across the capacitor, across the resistor, and across the electronic controller will be 12 volts. The reason for this is they all are connected in parallel. And we know when your components are connected in parallel, the potential difference across them is equal to the EMF of the battery. That is your Kirchhoff's voltage law. Okay? So the potential difference across all of them is going to be equal to 12 volts. Right. Now, once you open the switch though, okay, this is when the switch is closed. And when you open the switch, it's not going to be 12 volts anymore. So now what's going to happen is the capacitor will now discharge when the switch is open. So the capacitor will discharge, and it will discharge through the resistor and the electronic controller. So let's say initially the capacitor has the 12 volts, okay, because it's fully charged. That means the potential difference across the resistor and the controller is going to be 12 volts. But we know that the voltage across the capacitor, the voltage of the capacitor is going to decrease like this, right? And that also means that the potential difference across the controller and the resistor is also going to decrease. Okay, so the voltage of the capacitor will decrease, so the potential difference across the resistor and the electronic controller will decrease. Okay, and that's why it's going to last for a short amount of time, because the capacitor has enough voltage for a short amount of time. After that, it's going to discharge fully and it's going to have 0 volts, so it won't be able to maintain the power. Okay, so that's kind of how we have to write the answer as well. So the capacitor stores electrical energy in the form of charge. Once the switch is open, capacitor discharges and supplies current, and the PD across the electronic controller is equal to the voltage of the capacitor. And the PD across the capacitor will be high enough to last a short time. So that's going to be your 3 marks. Okay? So I hope that's clear. Now in part B it says the switch is opened. Calculate the time taken for the potential difference across the capacitor to decrease to 4 volts. Assume the resistance of the electronic controller is infinite. The capacitance of capacitor is 47 microfarads and the resistance of the resistor is 470 ohms. Okay, let's first clear what does this mean, the statement. Assume the resistance of the electronic controller is infinite. So a component of infinite resistance means it behaves like an open circuit. It does not allow any current to flow through. So if we have I, or let's write it like this, V is equals to IR and I is equals to V over R. Okay, then that's going to be potential difference across the resistance of the electronic controller. So PD divided by, let's write it as infinite, that's going to be equals to 0. Okay, so the current across the electronic controller is equals to 0. So basically all the current or the capacitor will discharge through the resistor instead of discharging to the electronic controller, because the resistance of the electronic controller is infinite. So when we solve this question, and we're going to be using this equation, I'm sure you already know this, you've caught on to it, that we're going to use this equation. We're going to take the resistance of the resistor, because the capacitor will not discharge through a component that has infinite resistance. The current across that component, which has infinite resistance, is going to be equal to 0. The capacitor will instead discharge through the component that does not have infinite resistance, which is the resistor here. So in this equation, the resistance will be the resistance of the resistor. Okay, so I just wanted to explain that. Now, pretty much a simple question. Plug in the values. The V naught is going to be equals to 12 volts. V is going to be equals to 4 volts. And time is what we have to find out. R and the C are also given to us. So I've plugged in all the values. Now let's get the answer. So when you solve this, you're going to get T as 24.3 seconds. Let's write that down. 24.3 seconds. That's going to be your answer. In part C, it says us the switch is closed at time t equals 0 and then open at time t equals 20. Sketch a graph on the axis below to show how current I through the resistor varies with time t. So when the switch is closed, the current will stay the same, constant, because the potential difference across the resistor is going to be equals to 12 volts. Okay, so I already told you at the start of the question, when the switch is closed, the potential difference across the capacitor will remain 12 volts. Okay, so 12 volts is going to remain the same, right? So it's going to be a horizontal line, something like this, straight like that, and then it's going to decrease exponentially. So let's find this value here. So what we're going to do is V is equals to IR, and I is equals to V over R. That's going to be 12 over 470. I think that was the value. Yep. Let's get this value real quick. So that's going to be 25.53 times 10 to the power of 3 amps. And we can say that is 25.5 milliamps. Okay. So this is going to be 20, let's get 26 milliamps. And then it's going to exponentially decrease. So now to draw a bit of an accurate graph, we can use T is equals to RC, the time constant. 470 times 47 times 10 to the power of minus 3. That's going to give me 22.1 seconds. So after 22.1 seconds, your capacitor will have 37% of the initial current left. Okay, so that's going to be 20 seconds where we start, plus another 22.1 seconds, which is going to give me 42.1 seconds. So after 42.1 seconds, the capacitor should be 37% of its initial value. Of the current specifically here, because we're drawing that graph. So let's do 37% of 26. So let's find that out. That's going to be 9.62 amps. So 42 is going to be somewhere here. And if this is 20, it should be somewhere here. 9, right? Okay. 9.62. So it should be right around here, somewhere here. Let's put that. Okay, so it should be exponentially decreasing. Something like that. Not perfect. Let's try it again. Okay, so I've drawn it. Took a few tries, but yeah, that's kind of how you want to draw the graph. I will show you something in the mark scheme as well now. So first of all, horizontal line of non-zero from 0 to 20, 26 milliamps, approximate, exponential decrease. Approximately drops to 1/3, which means around 33% of the initial value after about 44 seconds. This is again approximate and about, so just be accurate with it, but not too much. It's just sketching the graph. And yeah, okay, so just some things. And this is the my scheme and the examiner report as well. And yeah, I'll show it separately as well. And yeah, that's all for this video.